For thousands of years, our approach to making things has followed a single, logical path: subtraction. When an early human picked up a piece of flint to shape a hand axe, they did so by chipping away the pieces they didn't need. This logic followed us through the industrial age. To make a car engine or smartphone casing, we take a solid block of metal or plastic and we mill, drill, and grind it down until the final shape remains. It is a process of refinement through removal, but it is also a process defined by inherent waste and physical limitation. The factory of the last century is a place of massive, specialized machines. Each machine is designed to perform one specific task: stamping a sheet of steel or turning a bolt. This efficiency allowed for mass production, but it made manufacturing rigid. If you wanted to change the design of a product, you had to rebuild the entire assembly line. This created a world where we produce millions of identical items in central hubs, then spend enormous amounts of energy shipping them across oceans to reach the people who actually need them. Additive manufacturing, or 3D printing, reverses this ancient logic. Instead of starting with a block of material and removing what we don't want, we start with nothing and add only what is necessary. At its most basic level, a printer follows a digital blueprint to lay down material layer by layer, often thinner than a human hair. Because the machine only places material where the digital file dictates, we are no longer constrained by what a drill bit can reach or what a mold can release. We are moving from building to growing. This shift in physics allows us to create geometries that were previously thought impossible. Consider the gyroid or the lattice structure: complex, honeycombed patterns that are hollow yet incredibly rigid. In traditional manufacturing, creating a hollow, interlocking internal structure is nearly impossible because you cannot get a tool inside a solid object to carve it out. A 3D printer, however, views the internal empty space as just another part of the blueprint. We can now create parts that are 60% lighter than their solid counterparts without sacrificing any structural integrity. In nature, we see this efficiency everywhere. If you look at a cross-section of a bird's bone or a bamboo stalk, you won't find solid blocks of material. You find optimized networks of fibers arranged to handle specific stresses. Engineers are now using generative design software to mimic this. The computer runs millions of simulations to determine exactly where a part needs strength and where it doesn't. The resulting shapes look organic, almost skeletal. These parts cannot be made by a mill or a lathe. They can only be realized through the precision of a printed layer. The evolution of the materials themselves is just as significant as the machines. While early printing was limited to brittle plastics, we can now print with aerospace-grade titanium, carbon fiber, and even living cells. In a laboratory setting, bioprinters are laying down layers of bioink to create scaffolds for human tissue. In the construction industry, massive 3D printers are extruding specialized concrete to form the walls of houses in a fraction of the time it takes for traditional framing. The printer doesn't care if the wall is straight or curved, the cost remains the same. This technology threatens to dismantle the traditional global supply chain. Currently, if a specialized valve breaks on an oil rig or a remote farm, a replacement must be ordered, shipped, and flown across the world. This requires massive warehouses full of spare parts that might never be used. In a printed future, the warehouse is digital. You don't ship the physical object. You ship the file. The part is printed on site exactly when it is needed. This distributed manufacturing could virtually eliminate the carbon footprint associated with long-distance logistics and storage. We are now entering the era of 4D printing. The fourth dimension is time. By using smart materials, polymers, or metals that respond to external stimuli, we can print objects that are programmed to change shape after they are manufactured. Imagine a flat-packed solar panel that, when exposed to the heat of the sun, automatically unfolds into its optimal configuration, or a water pipe that can expand or contract its diameter based on the pressure of the fluid moving through it. The material itself becomes the sensor, the actuator, and the machine. This shift also offers a path toward a truly circular economy. In our current system, recycling is difficult because products are made of many different materials bonded together. However, a 3D printer can often create a complex object out of a single, high-performance material. At the end of its life, that object can be ground back into a raw filament and fed directly back into the printer. The factory of the future might not be a massive complex on the outskirts of a city, but a small, quiet room in your neighborhood that turns local waste into new tools. The end of the traditional factory doesn't mean the end of making things. It means the end of making things the same way we have since the Stone Age. We are moving away from the era of mass production and into the era of informed production. When we can print anything, anywhere, the value of an object shifts from the physical matter it's made of to the intelligence of its design. The future isn't something we will build with hammers and drills. It is something we will cultivate, layer by layer, from the ground up.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.